This is a demonstration of the rub IC and the eval board. You can see here on my fingers the tiny rub IC. This basically in its simplest mode is a RF bridge rectifier, ultra low loss. And what we've done, we've mounted the rub IC onto a DIL carrier so that the DIL carrier can then be used easily to plug into the eval board in the place of the rub, which is over here. Here we have a setup that's designed to show the efficiency of an RUB IC versus a standard bridge rectifier. What we have is an external power source, RF power source, constant current, generated by RAIS. It's feeding into channel 1 of the power analyzer and measuring the input power to the diode bridge. You then have an output capacitor, very small, but it just proves that you can have an output capacitor, which you can't do with a cross-coupled FET chain. You then have the output of the bridge going into channel 2 of the analyzer and onto a low voltage LED, sort of a 9 to 10 volt LED. And you can see here how much efficiency drop is lost by those diodes. These are standard RF diodes, and you can see you have 10.9 volts in and 9.2 volts out. That's the voltage drop of the two diodes on the bridge, making an efficiency of 84%. And this is driving roughly 600 milliamps, as you can see here. And here we have now, instead of standard RF diodes, these are now very high quality Schottky diodes, far in excess of the cost of the actual RUB IC itself. And you can see here the efficiency has risen to 91%. We've got 10 volts in and 9.2 volts out. So it's a vast improvement. Of course it's large in area and expensive. Now we have a single RUB IC. You can see the tiny size of the IC. And this now has increased the efficiency. If we go across the power analyzer, you can now see we're up to 94.5% efficiency. 9.63 volts in, 9.24 volts out. So it's reduced the drop to almost that of a single Schottky. And also, you'll note, we've got quite high currents going through the RUB. It can switch at an amp peak. And the great thing about these RUB ICs is that you can actually multiply them up. You can just keep adding in parallel the RUB ICs to generate, just as you do FETs, to generate an even lower, even better efficiency or lower voltage drop, which I'll show you next. Now you'll see what we've done. We've taken the RUB IC, we've literally stacked one on top of the other, which is very crude. We'd actually not need all these external components, there's not many anyway, but you wouldn't need them, you just literally have the two rub ICs. But you can see this crude demonstration already. The efficiency's improved again, 9.47 to 9.24 volts and 95.67%. A point to note is that this is quite hard to measure. Even if we had the perfect wire in this, we'd probably only be at 97-98% in this particular setup. So the rub IC is very low loss in this example. Now we're going to talk about some special modes that the RUB has. One of those is called half power mode. The RUB IC itself has a band gap reference inside it, and it has a comparator, two comparator inputs, and you're able to use those comparator inputs to reference against the band gap. And when it hits that band gap voltage on the comparator, it can change the mode of the IC, so you can enable the half power mode. For instance, you could enable half power at the peak of the mains to cause the IC to drop into half power. You could do it for some kind of output condition as regulation, you weren't happy, or you could do it for, say, temperature. You could be monitoring a temperature outside, think this LED is getting hot, I now want the lamp to be driven at half power, which sends a signal to the person saying you're running this lamp too hot, and also protects the LED. You could also do it at each phase of the mains using some special features of the half power. But in its basic mode, we've basically got just a little tiny resistor to show that we're going to adjust the voltage on the comparator. And if you look now, when I short these, when I connect this resistor to this lead, I will show you what happens on the analyzer. So basically you can see at the moment you've got 4.9 watts out or 5 watts out and sort of 540 milliamps. As soon as I connect it to half power mode, the wattage immediately halves and the current halves, whilst the voltage stays the same. You can do this on the fly, you can do this every half resonance cycle, so if you're running at 100 kilohertz, you can get a 200 kilohertz resolution in terms of bringing in and out of half power, which allows you to regulate a resonant circuit without changing its resonant frequency and without using deadband, etc. And the beauty of this is that the output bridge can actually then control or force what the resonant circuit does that's feeding it without any form of feedback back to the resonant circuit. So if you put it into half power mode, the RUB says I actually only want half the power, and the resonant circuit will just inherently provide that at half power without any coupling back to the resonant circuit. Okay, here we have now the RAIS and the RUB working together. The little tiny RAIS IC is here, and the RUB IC is here. Again, L1, L2, L3, and then C1. These three are the basic resonant components, and this is the input inductor for the filtering. Notice there's no X2 or complex CMC common mode filtering. This board, you'll notice it's exactly the same IC. We've just changed the inductors types from the 50 volt board you saw earlier. We just changed the recipe of the LCL components and impedance matching, and we can then drive other voltages. This now will drive sort of 12 to 18 volts as a setup. And we'll go now and turn this on and show you the performance on the power analyzer. Right, here we have the power analyzer showing what's going on. 230 volts in, 29 milliamps with a peak of 45. Power factor 0.93, running at nearly 82% efficiency, driving 17 volts, 325 milliamps on the output, with a peak current of 495. Notice here we have a fairly flat input current, which gives us the ability to keep the capacitance low and the dimmer compatibility. Now on the efficiency, the 81-82% efficiency, we can, with the RAIS technology, have a far higher efficiency using much bigger external FETs and more expensive components. We've cost optimised this to reduce the size of the IC to be as small as possible. And as you can see, it's very, very tiny. Now the IC is scalable. We could produce larger versions which would give us higher efficiencies, but we believe that, you know, the 4% maybe you gain, 5% is not really worth it against the cost saving and size of component reduction you get on a board. So we've gone for these small die sizes to produce the perfect IC for inside a tiny lamp. Okay, here we have the eval board set up in a way which allows us to set up the LCL resonant components. We've used the auxiliary supply coming in at 15 volts DC, which allows us to use any kind of supply on the input. Here we've got 230 volts DC. This red line here, we're measuring the current through the L1, through the tiny inductor, and the green wire here, or grey with green tips, lets us measure the current through L2. And the scope here on channel 1 is measuring the output voltage of the RAIS IC. If we go across to the scope here, you can see the current through L1 is the blue trace. You can see the points at which it crosses 0, and after just the FETs start to turn on. You'll see again the voltage is already at the point where you want the FETs to switch on, and the current is 0 as well, makes it very efficient. You've got a nice slow slew, which is good for EMC and common mode. And you'll see we've also got a very small current through L1, which is really good for using low-cost internal FETs inside the IC, high RDS on. It keeps the IC package small, the cost point low and the efficiency high, which is a very, very nice feature of the RAIS topology. If I now freeze this trace, And I switch across to now look at the current through L2. You can see the current magnification taking place. So there's the original L1 current, and here's the L2 current. I hope you've enjoyed this brief video on the RAIS and RUB technologies. Please go to our website for any further questions and technical reports, www.verdisemiconductor.com. Thank you.